Hello, welcome back. Today we're going to work on, and you're all smiling today. Everyone's in a good mood today. That's nice. UDP, TCP, maybe not RMI yet. This is a two-part. If you haven't noticed, this lecture is 111 slides. There's no way I'm going to cover it all today. I'm going to get through about half of it. Well, if I'm lucky, half of it. We'll see how long-winded I am. So what are we talking about today? We're talking about, and so there's a lot of repeat in this lecture as well, because if you've never taken an undergraduate course in networking, here it is in 111 slides. We got everything you ever needed to know about networking and all the problems with networking and the different types of architectures. And so I'm going to breeze through it at the speed of light sort of as a review and then hit the UDP TCP concepts. And a lot of you are wondering, why in the world do we need to hit UDP and TCP anyway? Well, because they're core networking technologies and they're the foundation of RMI, actually. RMI, believe it or not, uses both of the components, and RMI is a middleware built on top of, and actually it's a different level of abstraction on the underlying concepts, all running on IP. So part of the lecture is going to be on IP, which is networking and internetworking, part on inter-process communication, part on distributed objects, and then remote invocation, which is where we're leading to. UDP, TCP, and then the RMI and how that fits in with Java. So RMI actually takes care of a lot of these issues. However, that doesn't eliminate the possibility, and it doesn't remove the concept of the distributed system in terms of the architecture. It creates a nice distributed environment. So in terms of networking issues for distributed systems, one of the things that we need to address, especially when we start creating applications. In the previous networks, we had to meet simple application requirements. If we wanted to transfer a file, we needed to use a FTP. If we had remote login, we had to use a remote telnet program. We had email, news groups. It's all different applications that we're using to do all of these things. And so in a true distributed environment, they should all be blended together. So modern day applications blend them all together, so they're seamless, and the functionality just works together in a common middleware platform instead of having all of these different technologies. And most of the different technologies really didn't run in a distributed, ran more of a client server. The client, email client, still, believe it or not, connects to a email server, a POP server, or an SMTP server, or IMAP, whatever protocol is being used. It's still connecting to something from a client to a server perspective. So we can't eliminate, the concept that client server still exists. It does. It's part of our distributed environment. So UDP TCP creates client server computing. Actually creates the connectivity between the client and the server. So with the growth of the internet, more stringent requirements are necessary. New modes of use, additional or more stringent requirements have come into place. So when we talk about, and this is what I call my review of your undergraduate course in networking. If you've never had it before, this is brand new. If you had it before, these are some of the things you should have focused on. Performance is an issue. Speed, within which individual messages are transferred between the two different interconnected components. We measure performance in latency and data transfer rate. So one of the reasons why we use RMI is because it gives us better performance in terms of latency, less latency, higher transfer rate, less overhead in terms of the activities that are occurring. So in terms of latency, this is the delay that occurs after a send operation is executed and before a data actually starts to arrive at the destination computer. It would be network latency. The data transfer rate is the speed at which the data can be transferred between the two computers at the network once the transmission has begun. Data transfer rate is bits per second. It's measured that way. So we have message transmission time, which is latency plus the length divided by the data transfer rate. Obviously, the longer the message, we have to figure the transfer rate associated with the length of the message. Add it with the latency, and then we have the message transmission time. Another term that we often talk about in terms of distributed systems and issues associated with it is the scalability. Potential future of the internet is, commensurative with the population of the planet. As more people grow. Actually, what is our population growth? Are we still growing on the planet? Yeah, I think we are. Every year, the planet, we get more and more and more people. Even with all of the disease and everything that goes on in the world, we still get higher population growth every single year. Pretty soon we're going to outgrow the planet, I think, right? Isn't that what they keep saying? Well, it's kind of the same thing happening with the internet, believe it or not. Every year, more and more people are still getting on the internet. Brand new people never been on the internet. Because people are born. Population growth, I guess. I don't know. Unless they're born now with internet connectivity and strollers and cribs and well, actually now they have them in cars. So you play with the little video thing and connect to the internet with that thing. Download videos. So. Alright, so the size in terms of scalability indicates the size and the load of the internet. Networks must scale in order to be functional, so scalability is an issue. Reliability as well as security. Reliability is the degree in which the applications can recover from communication failures. RMI actually has got some really nice troubleshooting, and it is actually fairly reliable as a protocol. Security, that's always that is always a lacking thing. No matter how hard we try to make security, it's always an issue. Will always be an issue. So techniques for achieving security in a distributed system are, obviously firewalls, perhaps distributed systems with secured network environments, security on the end-to-end points, encryption, all sorts of things get added to it. Our biggest focus nowadays is mobility, having the distributed network. And I talk about distributed networks, it's the internet. The internet's the biggest distributed network out there, and it happens to be becoming the network. So we have network aware, which is internet aware, appliances, tablets, computers, cell phones, watches, everything connects to the internet these days, which gives us the mobility component of it, meaning that we have that connectivity without strings or without, it's not necessarily referring to wireless, but devices that can move around. Computers where you can connect to a cloud wherever you are and you have the same interface, same files, the same location. So wireless networking, providing connectivity to devices such as laptops, cell phones, PDAs, addressing and routing schemes for the internet. So quality of service is also one of the things that we look at in terms of measuring and looking at issues associated with networking, especially in the distributed environment. Applications that transmit multimedia data require greater bandwidth and latencies. Multicasting as well, one to many, many to many, needed for distributed systems in terms of current requirements. And now I'm going to go even faster because you guys should know all this. If you don't, if you've never had an undergraduate course in networking, this is what you were taught. So read through the slide on your own. Be sure be familiar with the different sizes of networks at this point. If not, go ahead and read through it. And the concept of internetworking, and what I just skipped through was basically some definitions on the different sizes of networks. And we're actually considering all different sizes when we build applications, which is how scalability works into the big picture. And the concept of internetworks, meaning the creation of the internet, which if you think about the concept, it is an internetwork, abbreviated internet, because it is accumulation of smaller network systems combined together in a distributed environment. So systems work with several different networks that are linked together to provide the common data facilities that are provided. So there's not just one computer that we're connecting to. We're connecting to a ton of computers server to server, which is giving us that network technology. So you can also read through the performance specs. If you have never heard of Bluetooth, you have never heard of Wi-Fi, you may compare the different, and each one of these technologies, and the reason why this is out there is kind of make you aware that the fact that we are still using a lot of different technologies, and these different technologies have different characteristics, they have different ranges, different bandwidth performances, different latencies. We put them all together on one network, and then we've got some pretty interesting combinations, and we're only as strong as our weakest link, if you think about it. So if there's a cell phone that's got a bad signal and it's providing a file that you're downloading, if you're doing a peer-to-peer kind of thing, you might as well just disconnect and reconnect, which is one of the issues, actually, when you think about it. Can't guarantee that everybody out there is going to have the same quality of service, same bandwidth going through. Going back to the concept of cell phones, actually, we're all familiar with what Verizon is doing now with the 4G Lite. It's nothing to do. It's 3G over fiber optics, landlines between towers. So what they did is they fixed the link of the slow connection between the towers and slow connection between the server hosts. They just laid fiber optics between them all, and now that was the slowest part because that was slower than the 3G service. So now we have 3G over fiber between the towers. So the cell is still 3G, but the ground, which is why they can't call it 4G, it's 4G LTE, for fiber optics. Well, the light, LTE is abbreviation for light. So fiber optics is light going through glass tubes as cables between the towers. So anyway, long story short, it's kind of interesting how they played around with that. So I'm still waiting for 4G to come out. So. Protocols. This is what we're talking about in terms of network protocols. So it refers to the well-known set of protocols and formats. Those are the rules. We have two parts to the protocols. We have the specification, the sequence of messages that exchange, and the specification of the format of the data and the messages that go. And here's the lovely message the lovely chart that everybody loved when they took their networking class. This is sort of representing the model of the protocol exchange, or the concept of layering in protocol software. And there's only really about two strong models in the States, the DoD model and the OSI model. So if you took your undergraduate networking course, you hated this part of the chapter because it was a bunch of memorization of the different layers of the models and how the layers work with each other and which layer is responsible for what responsibility, blah, 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 blah. Well, as an application developer in the Java EE course, it's nice to know this stuff because then you can see what layer your technology is actually working on. So I'm not going to go through and I'm repeating your entire networking course, but as review, it's a layered system. So that message from A, sender, goes to message to B, receiver, follows communication medium, depending upon the layer, depending upon the protocol being used for each component. And I'm not going to call it application, but each component in the layer. So in terms of the layering, it's a hierarchical structure where each layer represents an interface to the layers above it and below it. So sending side accepts the top item. So each layer except the top layer accepts an item of data or something specific from the layer below it or above it. Well, actually above and below. It's usually below goes to above, below goes to above, below goes to above. Because if you kind of think of the concept, actually, how many people actually remember the OSI model? How many people learned it with 7 instead of 5? Originally 7, yeah. It was 7 stages. The only way I remember is all people seem to need data processing, application presentation, and and then they moved it down to 5. Current textbooks shortened the OSI model to 5 layers. Got rid of session and transport, or maybe it was networking and session. I think got rid of session, moved it into one of the other ones, and they got rid of another one. Like I want to say it was the data link layer or something. I'm not sure. But how can you remove that stuff? I think they thought that 7 was too complicated. They shrunk it down to 5. Well, actually they did that because the DoD works with 5, and so they tried to make the two models compatible. They come from 2 different sources. We're talking about 2 different perspectives on it. So if you're not familiar with the Department of Defense, the DoD model, it's just like the OSI model. It's a variation of it, but it's compatible. In fact, you can map from DoD to OSI from the 7 layer. You can't map. It's supposed to mimic the 5 OSI is supposed to mimic the 5 DoD. Which, I don't know, it's like going back and changing math. Here it is here. All people seem to need. But this is the 5. 1, 2, 3, 4, 5. This is the stripped down model now. The newest invention. So all people seem, we still got the seem, to need, well, we're missing the bottom. Okay, this is only the first 5 layers of it. So we're missing the physical and the data link that's on the bottom of it. But so this is the full model. It's just not showing you the last 2. The DoD actually has these guys combined in TCP/IP, because IP is the it's the network, and TCP and UDP, that's the transports. So and transport / session support, sending information back up to session. So if you think of the concept, it should be broken out. So anyway, the tags are the headers of the protocol types for each one of the layers needed to receive protocols correctly unpack each one of the packets. So really what we're looking at in terms of the sending side and the receiving side is the packet exchange. It's kind of like the U.S. Postal Service. You know, you have a from and a to address, and a stamp. Well, the stamp so you can pay for it, but the mailman knows where it came from and where it's going to by the addressing. It's a pretty easy lookup system, actually. They go by the zip code that's on the envelope. So it's kind of like the same thing where the receiver knows what the sender is sending it. And if you follow the protocol stack correctly, your messages actually arrive and they get put back together the way they're supposed to be put back together and stuff. And then we have packets. That was the other fun part. Ethernet packet and IP packets in the networking environment. And packet is just nothing more than the format that you're looking at. And I will have an entire lecture on packets and IP4 versus IP6, but not for another couple more weeks. So the protocol suite here, we got the complete set of protocol layers. It's referred to as the protocol suite or protocol stack. This is just the vocabulary and the OSI models, the reference to the open systems interconnection. And the internet, you might say, is based on, well, the internet is the transport, but it's the part of meets into this OSI model and also the DoD structure as well. So providing layering to substantial benefits to simplifying and generalizing the software interfaces. So also carries significant performance costs. Why do you think so? Well, because you have to add support for the communication between the layers. And you have to consider things that are not part of your protocol so that you can be compatible with other protocols. So, and here we got, this is 1, 2, 3, 4, 5, 6. Here's our 7 layers. Okay, good. So this, I'm pretty, yeah, as I remember the slides, it does go into the 7 instead of the 5. So if this stuff is brand new to you, go ahead and get yourself an undergraduate book in networking and figure out how to take a networking course. In fact, so this is slide number 18. Slide number 19 discusses slide number 18 in a lot more detail. Important note, however, is what I mentioned before, the TCP and UDP, which is what we're really talking about today in terms of protocols, following the transport, and they're running on top of IP, which is at the network layer. So, and here we are, TCP, Transmission Control Protocol over Internet Protocol. Grown now to over 60 million hosts. Okay, probably a little bit more since this slide was actually produced. Example application services and protocols based on TCP/IP. HTTP. Well, the entire internet, actually. I shouldn't say the entire internet. Most of it is TCP-based applications. So, the web itself, HTTP, is built on TCP. SMTP, POP servers, NNTP, network news, newsgroups, file trans, FTP, Telnet, all built on TCP. So the TCP layers, we have underlying network underneath it, the network interface, or network specific frames, IP datagrams. The datagrams and the streams are something interesting to note between the UDP and the TCP. The UDP TCP packets, and I'm going to get into that in a few minutes actually, that right above the IP datagrams, and then the messages or the streams. So the UDP message versus stream, which is interesting, which makes one of them, better suited for certain applications versus other ones not well suited. So the two transport protocols, and this is probably what you learned in the hopefully what you learned in the networking course, was the definition of the two of them. So TCP being the reliable, so it's connection oriented and it's more reliable. It's also more heavy overhead because there's message exchange going back and forth. It takes three messages to establish a connection. UDP takes one message to establish a connection. And there's a datagram protocol, does not guarantee reliable transmission. And then we have IP, which is the underlying protocol. And the IP diagram is nothing more than the transport. Excuse me, not the transport. It's the network that's creating the transport. Provides the basic transmission mechanism. So in layman's terms, this is a way I actually have taught undergraduate computer science networking, networking 101, beginning stuff. Here's UDP. You got two kids standing on opposite sides of a road. You got a road coming in. One kid's over there, one kid's over here, standing on the roads between them. UDP is you take the ball, they're tossing a ball back and forth. You take the ball and you throw it to the other guy. And it's not managed. You just tossed it out there, and you're hoping that the other guy over there is going to catch the ball. Probably going to have to run out of the ball if you throw it in the wrong direction. He might take a while to find the ball, who knows, but he might actually get the ball eventually. Especially if you throw it right at him, he's going to get it, right? That's UDP. Unreliable. No management to it. Very easy. You got to get rid of it. You know how many balls you can throw? You throw tons of balls real quickly. You get them all across the street real fast. TCP. The guy takes the ball, maybe it's a basketball, and you know how basketball people, they dribble? One kid follows the ball, dribbles it from one side of the street to the other side of the street, and hand delivers the ball, or bounces it right into the hands of the other person, and then has to walk all the way back to the other side of the street to return to the original position to send another ball. Very slow, because he has to take the ball, dribble it to one side of the street, and he's managing it. He's micromanaging the ball. He's controlling where the ball is going. The ball is completely in control. We know if the guy made it or not, especially if he comes back and he gets run over by a truck. He never shows up again. Well, we got to go send another kid with a ball because the ball didn't make it. So we know we have confirmation when the guy returns alive that the ball made it there. So it takes a lot more work and it's slower because we got to wait. We have all that latency time in terms of the network. So, and the IP is the road. It's the path that's paved that's creating the connection between the two kids. So, and I have another way of describing this too. It's with sushi boats, but it usually makes me hungry and it's right around lunchtime. Because if you think about a sushi boat restaurant, where the boats go around in circles in water, and the boat is actually the IP, and the pieces of sushi are the datagram packets. The datagram packets float around on sushi boats. And then the people pick them off. Oh, I like this one. Oh, I like that one. And then they assemble a meal out of that. So that's sushi. That's IP, Sushi Network. All right, that may be fun actually, but go to a sushi IP bar. Internet protocol, usually layered over other protocols such as Ethernet. Oh, Ethernet's a totally different story in itself. Ethernet works without IP, by the way. We have Ethernet networks. Actually, a lot of things worked before IP came around. So, Ethernet header. The internet, however, was not going to work without IP. Ethernet packets can switch around in an IP-like format. There's a separate Ethernet packet format, completely separate Ethernet frame. Or we have the IP header that would go on a TCP packet, or we also have TCP headers that includes port information and it comes up to the message. So in terms of the abstraction, we have this encapsulated in the message itself that's transmitted via TCP over the Ethernet line. We have all of this stuff working simultaneously. So underneath the IP, we actually have the Ethernet packet format if we're running on an Ethernet network. So here's how it works. IP on the bottom. We are either running with TCP or we're running with UDP, and we have applications that run on top. In terms of the addressing, right now we're on a 32-bit IP4, and we're still IP4 backward compatible because the world hasn't switched to IP6 yet. Otherwise, you're asking everyone to throw away all of their equipment and upgrade. Probably not going to take another 20 years before some of that old equipment actually gets replaced. So you want to keep compatibility going on, so you support both. So, scheme chosen for naming and the IP routing and the IP hosts. So, assigns IP addresses to each one of the hosts. It's 32-bit numerical identifier. We're all familiar. There's a 192.168.1.1. What's that? That's a router. Yeah, that's usually a router address on a network. And here we go. This is another review. I can kind of skip through this. Different classes. In fact, I have a lecture coming up that's going to get through all this stuff. So UDP and TCP provides the communication capability. So in the form of useful application programs that we write. And I'm going to get to the application programs momentarily. It's coming up extremely soon. So we accomplish it using ports. So we load the protocol from the Java API, networking actually, NET, and we bind to ports so that we are transmitting it through a layer of abstraction that's around the port, that's associated with the port number. And we use the port and the port numbers as the addressing for the messages so that they can be processed back and forth between valid computers. So once the IP packet has been delivered to its destination port, the TCP UDP layer dispatches it, processes it via a specific port at that particular host. So we need the host, we need the underlying IP to be running, which we have on all of our computers actually. We can open up two terminal windows, start our server on one end, bind it to a port, start a client on another end. We don't even have to bind it to a port. We just have to send out at any port we want to the port where the server is sitting on. So we have to specify where we're going to send it to. And it goes through the encapsulation of all of the data transmitted, through the OSI model from the IP all the way up through the TCP or the UDP, and encapsulates all the information and then delivers it through the port. So, which is what we're going to see. So in terms of UDP, we're talking about a datagram that's encapsulated inside of an IP packet. Everything flies inside of IP packets on an IP network. Short headers with source and destination port numbers, length of the field, and a checksum might be associated with it. UDP does not guarantee delivery, adds no additional reliable mechanisms except for the checksum, which is optional actually. So it's throwing the ball across the street. And we use it to restrict is restricted to applications and services that do not require reliable delivery of single or multiple messages. TCP, on the other hand, is more sophisticated. As we mentioned before, it's dribbling the ball across the street. Provides reliable for long sequences of bytes. Bigger messages can be sent that way more reliably because they're actually going to be delivered, hopefully. So UDP is actually kind of nice for small stuff. UDP, email is an example of that sort of, but it uses a different protocol built on it. Different protocol stack, but similar in concept. It is UDP. TCP is constant connection. That's like what you did. In fact, in the old days, if anyone remembered connecting to the internet through a dial-up modem, you had to add on TCP to your Windows machine. You had to add on, actually, what was it? TCP and something else. You had to add on to your networking and then bind it to the address of your Ethernet card. And it was actually kind of complicated. Now you just plug a cable in your computer and you have internet access. You don't have to do any of that setup. But we have a guarantee that the receiving is actually done, and once we get the confirmation, we can actually resend again. So TCP has the ability to resend messages. Sending the processes in the same order, so the packets are kind of going in a more structured order versus just throwing it out in the street. If you think of the concept on a UDP, if I threw 10 balls across the street, it may not arrive in the order in which I threw them, because one of the balls I may have put a little bit more pressure on. Whichever ones I throw the hardest, probably going to end up going there faster. So if I did 1, 2, 3, I might get 3, 1, 2 received in that order. So the order is unpredictable. TCP is more predictability because it's more managed. We know that we're going to have this sent, and then we're going to have this sent, and we're going to have this sent, because we're getting confirmations back, and then we're able to resend if it's not received. So a little bit more management. So how does this fit with RMI? Let's take a look. So looking at the IPC from the programmer's point of view or perspective, what we got on top of it is RMI and RPC. So this is the old style Unix protocol, the remote procedure call, which we actually have in Java, and we can program with that. We're going to take the RMI route because it's on the same level. What we have underneath here is this middleware layer. So the underlying protocol is running through UDP TCP. Combination of both, mostly TCP actually. So the RMI abstraction, the remote method invocation, is running on top of the marshalling, external data representation, the request reply protocol, all of the different things that people often refer to as middleware. But we still have this protocol in place. It's running on top of it. But it's loaded automatically. We don't have to program in it. Instead, we just start up RMI. And a lot of the automation actually with RPC and RMI as well is the automation is done kind of seamless to the entire underlying protocols that are underneath it. We don't have to, we don't create the port. Well, we actually do kind of use a port in terms of an abstraction, but we don't think about that in terms of starting the engine. Do we know what RMI actually means? Are you guys familiar with the concept? Remote method invocation? Okay. What does that mean? Instead of running an object on your computer, you're running an object on another computer. So, can you imagine, in this day and age on the UDP TCP, we're sending messages back and forth. It's the sending and receiving of data. In an RMI, we're calling another computer. We're not really sending information, we're sending a request. Say that one more time. No. Totally different. In a UDP TCP, which we're going to look at first, we're sending messages back and forth, and the message is received and sent, and we're using the data on both ends. In an RMI, we're still doing that, but what we're sending is a request. And the request is to receive a service from an object that resides on another computer. So, when you built your first Hello World application, you run it on a JVM on your computer, Java Virtual Machine. And the virtual machine organizes all the class files. Those are the objects. So Hello World might open up and make an instance of the class Hello World. Might make an instance of another object. I have to get past Hello World to actually have multiple objects. But all those objects are loaded on your single computer. Now take all those objects and put them on other computers on the network. And now call them remotely instead of locally, and you got RMI. So you actually have to load up an interface. You have to start what's called an RMI server module first, or an object that has an interface to it. And your client connects to the object through the interface. And the interface is our public-private protected, if you think about the concept of the interface. This is like a C++ or Objective-C concept, actually. Our specification, our interface to the object telling us what's available to clients. So the structure itself sends and receives through TCP or UDP. What happening on the RMI end is the method invocation. So you're running methods on objects that don't exist on your computer. They exist on other computers. And the communication is facilitated through UDP and TCP as an underlying protocol. Underneath the request-reply protocol and all of the security features, which is not in this slide, but marshalling is in this slide, which is good. We'll talk about that when we start looking at RMI, because what you'll see in the RMI, error messages or marshalling issues, that's pretty much all you're going to see is exceptions due to marshalling, which just means it can't find the object. The request broker it's not there. You're not calling it the right location. It's not loaded correctly or something. And I'll talk about that next time when we start looking at RMI. But in terms of the inter-process communication, we're running a form of IPC. We have one thread on one computer connecting to another thread on another computer or another client versus a server. And that really gives us that exchange and that synchronization. So archiving in terms of synchronization, reliable exchanging of the data. Amongst other types of different processes, we have shared variables, message passing. We have all sorts of different concepts, concurrent programs that are running, concurrent processes, and different operations that are running. So what I want to do is demonstrate to you the UDP and the TCP. And I'm going to kind of skip ahead, but this is really a three-part. I'm going to turn this into a three-part. So I'm going to go back. Hopefully my TA will remind me. I want to go back to IPC next time, cover a few more things related to that, because I've already given you a lot of theory today. And I want to kind of take a look at the sockets, the ports, and the protocol, so we can get through those examples, because it'll give you something to work on. So in terms of the sockets and the ports, we're looking at a client and a server, and what we've got here is a socket that's created on the client, a socket that's created on the server, and the socket is bound to a port, and it's agreed upon port. On the client, it doesn't matter what port they use, any port works. But on the server, we're going to say like a port number that we're going to connect to. And then we're going to send a message back and forth. And we might have other ports out there that aren't being used that are just open. Or they might be closed. It doesn't really matter. But we have an internet address over here. We have an internet address over here. We're not going through IP, though. We're going on top of IP. So if we go through UDP or TCP, we're sending and receiving back and forth through through a higher level a layer of the OSI model, actually, through the TCP. And we're letting the TCP or the UDP control the communication, which is kind of the purpose of going through this as an example to sort of look at it. Remind me, and we're going to go through this example, but I'm going to go through the rest of the slide, don't worry about it. Let's take a look at UDP in action so we can kind of put this into perspective. So in the file that I've got downloaded here, if you unzip it, it's going to be called S-code. Oops. And in the S-code, there's 4 different programs in here, as you can possibly see here. We've got, I'm going to clean this up in a few minutes. We have a UDP example, a TCP example, a RMI example, and then an RMI using a service. Well, we had 2 RMI examples. I'll get into that in a few minutes, but or I'll get into that next week. But if I go out to a terminal prompt, and this will work the same way on Windows as it will work on this Mac, so it's the same concept. And let's see, if I change the directory to desktop, which is where I have the file loaded, and change the directory, S-code. Looks like I have the, I'm going to delete class files. No, actually, you know what? I'm just going to leave them alone. That way I don't have to compile them. If you compile the examples, which should compile just fine, because next time, I'll wait until next time before we go over the source code. I just kind of want to demonstrate what it is we're going to see next time. And if you bring your computer, you can actually run through the examples at the same time and sort of see it work. But in terms of what we're trying to accomplish here, what we're going to do is I'm going to load up the UDP. We're going to look at UDP first. I'm going to load up the UDP server, which is going to be called UDP Simple Server. And it's going to sit there and it's going to wait. And the UDP Simple Server, actually, I'm going to bring up JGraph so I can show you the code for UDP Simple Server. I believe this one is going to be bound to port 7777. I just want to check real quick because I have to know what port I'm going to actually connect to. Let's see, RMI, we don't want RMI. UDP Simple Server. UDP Simple Server. Or Server Simple, here we go. There we go. This is our first example, and yeah, it is 7777. So what we've done here from a programming perspective is we're including the network, we're including the I/O, which is, this is as basic as you can get, actually. And we're creating a class or an object called UDP Server Simple. And it's using a datagram socket as the socket. The datagram socket is just nothing more than an abstraction of something that's going to bind to a port and receive datagrams. And take those datagrams, and we can run methods on the datagrams. So what we're going to do is create the server port as 7777. And we're going to bind the socket to the port by going, the socket is equal to the new datagram socket for 7777, which is the internet. The integer value that I've set to the server port. And then we're going to declare a storage area for the received data, because the datagram socket is just nothing more than the abstraction of receiving datagram information. That's going to fly over IP for us automatically. And declaring you know, this buffer here that's going to store the bytes that's going to be in that information that we're going to receive. And it's going to say waiting for the incoming request, and then we're going to take the incoming request and create a new datagram packet out of it, add it to the buffer, which is that byte array that we created. And then take the socket.receive, receive the incoming request to process it, and then print received message, and then I believe it's all going to just print a message out to the screen. Incoming request at get length, and then it's going to essentially parse the information out so we can get the data, get the length, get the address, and get the port for where it came from. And then print out something, you know, reply sent, and then send a reply back to the client to say, hey, I received your message. So the server's going to sit there, wait, receive a message, and then he's going to essentially send something back after he's received something. So if I run it, if I can spell it correctly, UDP server simple. I see it waiting for incoming request. And then what I'm going to do is I'm going to pretend like I'm on a different computer on the network. So one of you can actually send me a message, actually. But I'm going to use localhost instead of, you know, I'm just going to use localhost, and I'm going to open up another window and do it this way. New window. There we go. And let's see, change directory to the desktop. Code. Perfect. And then on the client side, if we follow through, and the lecture actually kind of goes through each one of the things. So in the server, we don't have to say anything. It's just going to bind automatically to 7777. Hopefully that one, I haven't run anything today on that, so it should hopefully be open and free. And then on the client side, when I run it, oops, here we go. That's the server. Hold on one second. Skipped for some reason here. We went from UDP to TCP. Here we go. Here's our client simple. So what we're going to do is I'm going to use localhost instead of, in this particular example when we run it, we're going to connect to 7777, which is the port that the server is waiting on, listening to. We have bound a datagram socket to that port. On the client, I'm going to connect to, and this would assume that alpha was the name of the server. Well, it's not on alpha. I'm just going to use localhost because it's on my same computer. I could type in one of your addresses, 192. If I had your IP address, if you're sitting out in the audience there, and you could actually connect to me. If I gave you my IP address, it would go, because it's flying over IP. So you could actually connect to me right now and send me a message. But I'm going to do it on my computer. Actually, in the weekend class, we tested it out, and I had somebody actually send me a message, and it works. So, which is cool. Which means there's no security at all on this network. So back here, if I type in UDP simple, server client simple, and I type, I'm going to connect to localhost, and it's on 7777, and I'm going to send it hello from ITU. Then I'm waiting. I'm like, okay, what happened? So then I go back to look, see what happened on the server end. So I got the syntax correct. There we go. Where's my server? Waiting for request. Okay. I got a problem with Houston here. I don't have UDP simple client simple, server simple, client simple. Didn't connect. Interesting. Let's take a look, make sure I'm running the right client. UDP server, UDP client. Okay, hold on one second. It should have connected, actually. I've seen it connect before. Possibly I'm running the wrong client with the wrong server is what I'm thinking. UDP client. Either that or I'm not called localhost anymore. Yes? Hold on one second. Did I type the wrong one? No. UDP client. Did I type that correctly? UDP client simple. Well, that's the correct one. Let me take a look at UDP client simple real quick here. Make sure I have the syntax correct. Client simple. I was having a bit of a problem. I may not even have a network connection. I was having a bit of a problem. Client simple. There it is. I was having a little bit of a problem on Monday, actually connecting to the internet from my computer, but I believe I have a connection. I believe I'm not having any internet issues today. Let's see what we got here. We're supposed to take 3 arguments. Okay, good. Actually, this look at diagram, server port. Okay, good. It's just the port and the message. Okay, good, good. Let's see if it's spelled localhost correct. It should have taken it. It should have taken it okay though, which is kind of weird. It is unreliable though. So let's see. Localhost. Interesting. Well, I can't tell you why that's not working. I'm going to need to troubleshoot that a little bit more. Always something new on this network, though. Well, I did this a couple days ago for the weekend course, and you can watch the video on it. It actually does work. I think what I'm going to do, though, because I'm feeling pressured on time today, actually, too. Instead of spending time to troubleshoot this today, we've already kind of been here long enough, I think. What we're going to do is I'm going to troubleshoot this and test it before next week's lecture, see what has happened. Most likely I've made a change to it. Sometimes when I demonstrate stuff, I change the code and I recompile it, and I break something in it in the process, just to change a parameter or something, and then I go, oh wait, it's on 777 though. It should be connecting. The fact that I'm not getting anything is going to tell me either I've got a network issue or I've changed my local host, which is probably the issue. So my host name is probably bhacker is what I'm thinking. Actually, let me try that real quick. I've got another idea here actually. Oh, here's another problem right there. Ooh, here we go. UDP simple client. Oh, here we go. Wait a minute. I actually did not put a closing character on the end. We'll try it with localhost one more time, and then we'll try it with a different. Hold on a second. Where am I here? Oh, I'm in here. So let's see. Simple. Let's try localhost one more time. Localhost. 1, 2, 3, 4. Hello. There we go. See, the assignment works. Okay, so apparently I didn't close the string correctly, which was a typo. As you can see, I didn't put any error message in there, so it didn't actually. The client hosed because it couldn't find the string because I put a single instead of a double quote at the end of it. So it wasn't giving me too many error messages, obviously. So okay, there's a good example of the power of error messaging. So back here on the client, I sent the word hello. So excuse me, back here on the server. So I loaded the server, and you can see actually because I bounded the same port, I just loaded it a couple of times, loaded the client a couple of times. You can reuse the port over and over again. But here what I've done is I said, it was sitting here waiting for incoming requests. It received the request hello, and then it sent a reply sent, and then now it says waiting for incoming request again. So over here, sent the message hello, received a packet of 5 bytes from, and then here's the address. This is actually localhost, is where it's sitting. That from at port 777. The reply message was hello. Well, it sent me the message back. It says that the reply message. So if I ran it again as an example, I can say, hi there. Hi, if I spell it right, hi there from ITU. So now I can see over here, it said a hi there from ITU that came through on my server that sent it back to my client. So this is what we're going to be doing, and this is what you're going to be doing for your second assignment, actually, that works with UDP and TCP. You can actually use this code. It's called S-code. It's in a folder that's on bhacker.com, right next to the week 4 lecture, or the lecture 4, I should say. So I feel like I'm being pressured for time today, so what I'm going to do is sort of end at this point. I want to go through this code a little bit more for you, and I'll also run the TCP example for you. So I believe next time I should be able to do the UDP, the TCP, maybe run it from different computers, and then I'll get into the RMI. And the RMI you'll see is nothing more than this type of system in terms of the configuration, except for we're looking with different parts, and we're loading different objects in different windows when we set it up. So whether I load it on my computer or whether I run it from another computer, doesn't matter. It's all the same. except for I'm not going to be using localhost. So if I knew your IP address, you could load a server and I can send that to you. And just as a sort of a side comment, what does this sort of thing remind you of? Sending messages back and forth between clients and servers. It's instant messaging. So what do you do when you load a Yahoo Instant Messenger on your computer? You're sitting there waiting on a port to receive information. You send a message out to somebody in your list. You enclose it in that datagram packet. It goes to a server. On the server it says, B Hacker is sending a message to S-code. So the packet, when you send it, has the text message and who it's supposed to go to. The server takes the message, turns around, and sends it back out. Because you've got one server waiting on one port, and he is receiving information from several different clients connected on all these other ports. And he's the message exchanger. So the server in this, it can easily turn this into a really nice chat program, actually. You have one computer that acts like the server. All of the messages go to the server. The server turns around and sends it all back out to the client. And it's UDP, so it's fast, and it can handle many simultaneous connected clients. And all the clients don't know about each other. They only know about the messages that are being sent and received. So they know, you know when you've sent a message out to XYZ, and the server gets it and says, this text is supposed to go to XYZ. He turns around and through his port sends it out to the port that XYZ is, and you're attached to a port. So in one of my other examples I'm going to show you next week, is that the server is going to print out all the ports, all the port numbers of all the clients that are connected to. So what we get is we get an IP address for where your computer is, the port that you sent that thing out on. The client keeps track of that. Excuse me, the server keeps track of where the messages came from. And it's just an exchange. It's just exchanging messages between clients and it's acting as the middleman, routing the messages to the correct port and the correct IP address for where it's supposed to go, given your tag name that you created for yourself in your chat session. And the server keeps track of all of those. So when you download and you install your Yahoo Instant Messenger, if you haven't noticed, all that stuff's stored on the server. Get a brand new computer, you install Instant Messenger as an example. You say, would you like to use your settings? You log in and voila, there's all your clients. They're all other clients just like you who show up in a list. You click on them and you say, here, hello from ITU. Goes to the server. Server says, this belongs to S-code 99. He says, okay, S-code 99 is at IP address, blah, 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 and they're currently connected. Okay, good, and here's the message. Otherwise, it queues it up if they're not connected and puts it in a log for you. But this is the basis, and this is a good example of what UDP is used for, still being used for. It's not outdated. It was not replaced by RMI. But you can create a really nice text messaging program, instant messaging program using UDP. Because what is it? It's just simple text messages. You can also use UDP to send files and stuff too, but it's not as fast and it's not as reliable. It was never meant to store huge quantities of information. It's like for text and for messaging back and forth. So, anyway, I hope you enjoyed the example, and next week we will continue. I'm not done with the examples yet. Just started. I was talking too much about the assignments earlier. So next week we'll continue with UDP, TCP, and finally, eventually get into RMI, which is where we're headed. Any questions? No? Okay, see you all next week. Thank you. Take these servers down. Take the client down. Client is down.